Hello guys, welcome back to another video on my channel. In the last couple of videos, we have been following this linear algebra lecture series. We talked about the different kind of algebras, their overview, and motivated linear algebra in the first video. In the second video, we defined vector spaces and vectors rigorously. So in this video, we're going to talk a little bit about subspaces or subsets of vector spaces and things you can do with them. But before we start, I have this interesting bit of word etymology for you guys. The word vector actually is Latin for carrier, which traces back to the Latin verb vehere, which means to convey. And I'm certain that the prefix here ve actually traces back to the Proto-Indo-European for travel or carry, and is essentially the same root for words like vehicle. So, with this interesting bit of etymology, let's get started. In the last video, we explained what a vector space is by listing its properties and detailing the algebra it satisfies. So we can refine our examples of vector spaces by actually talking about linear subspaces. So let's define what that means. A subset U of V is called a subspace of V, where V is a vector space, if U is also a vector space with the same additive identity and the operations of addition and scalar multiplication as on V. So what this means is this is not only a subset, because not any subset is also a subspace. For a subset to be a subspace, it needs to inherit the operations of addition and scalar multiplication and the additive identity from V, and in a way that they're well defined on it. So mathematically speaking, if you map V, which is a vector space which has the linear algebra structure on it, onto this subset U, the algebraic structure will be preserved in that mapping if and only if U is a subspace. It won't be preserved for an arbitrary subset. That's the difference. And it's easy to check whether a subset is a subspace. And to do that, we just verify the following three conditions. Instead of actually checking that it's a vector space and satisfies all those, I think it was 6 conditions that we had for a set to be a vector space, we just need to verify the following 3, because the rest follow because U is a subset of a vector space itself and it's inheriting its algebraic structure. The rest will follow. The proof that the rest follow is, I would say, straightforward, but I'm not going to include it in this video because it will take away from the beauty of these 3 conditions. So additive identity is the first. You need to check whether your subset of a vector space has the additive identity included inside it. And again, this additive identity is inherited from the vector space V. You need closure under the addition operation. So if U and W belong to the subset U, then U plus W must also belong to subset U. And similarly, closure under scalar multiplication. So if F was the field that you had in the beginning when you had your vector space, say A belongs to the field and U belongs to subset U, A acting on U should also belong to capital U. That is what it means to be closed under scalar multiplication. So you have these 3 criteria. And again, to prove that these are indeed really all that you require for U to be a vector space in its own right is You can do that. I'm not going to do this in this video. So when we work with vector spaces, we will have several subspaces in the most general situation. You rarely work with just one. We attempt to join all these subspaces to form a larger one. And how will we join them? You might assume that since they're sets, you might try to take a union. But sure, that works if it's only a set or a subset in this case. But here you have subspaces, which means they're not just subsets, they're also subsets which uh, preserve the algebraic structure from the vector space that they're inheriting it from. So we did an operation that actually respects this algebraic structure and not just the set. So you see that if you take the union naively, as you would for subsets, then it doesn't work. The resultant of taking the union of all these subspaces is not itself a subspace. And there's a few examples you can think of. You can say that, well, I take two elements, take the union of them, but then if I take v plus w, where v belongs to one subspace, w belongs to the other, that is not guaranteed to be in the union, because the union is not necessarily closed under the operation of vector addition. So we need to define a different operation which respects the algebraic linear algebra structure. So we define a sum of subspaces. So what that means is, suppose v1 through vm are m subspaces of v. The sum of v1 through vm, denoted by v1 plus dot 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 vm, is the set of all possible sums of vectors of v1 through vm. And what this means mathematically, or more precisely, is that v1 plus dot 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 plus vm is actually just the set v1 plus dot 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 small vm, such that v1 belongs to capital V1, and so on, and vm belongs to capital Vm. So each of these individual summands here, they belong to the distinct subspaces that we had. So any arbitrary element of this this sum, the subspace sum, can be expressed as v1 through vm, where each v1 through vm belong to each corresponding subspace of v. An example of this is, take the following subspaces of f3, three-dimensional plane. So u is x 0 0. So this is like the x axis in your field. So this is an element of f3. This tuple is an element of f3, such that x belongs to f. X takes values in the field. And w is basically just the y-axis. So 0, y, 0. This tuple again belongs to f3, and y again belongs to the field. Then u plus w is just, using this definition, is just the tuple x comma y comma 0, which again belongs to f3, such that x and y both belong to the field. So this is the two-dimensional plane, the xy plane, if you will. That's an example of a vector space sum. We're summing this subspace u and subspace w to get u plus w. Now we have a proposition that, suppose v1, vm are subspaces of v, then v1 plus summed till vm is the smallest subspace of v containing v1 through vm. How do you prove that? Well, let's break it up. We first need to prove that the sum v1 through vm is a subspace, and then we have to show that it's the smallest one that contains v1 and vm, v1 through vm. So to prove that it's a subspace, it's straightforward to verify that. We just check that it contains the additive identity, the 0. It's closed under vector addition and scalar multiplication. That's all three criteria that we had at the beginning. Now let's prove that it's indeed the smallest one that contains the subspaces v1 through vm. So suppose for the sake of contradiction that there is a smallest subset of v that's not the sum, that's not the subspace sum. So the smallest subspace of v containing v1 through vm, let's call that b. So our set of inclusions go like v1 vi, sorry, for all I in 1 through m. So any one subspace we had at the beginning is a subset of b, which we're calling the smallest subspace of v that contains v1 through vm. This is what we assume by for the sake of contradiction, and since that's the smallest, that is a subset of v1 summed until vm. Now since b contains vi for all I, it also contains their linear combinations because it's a subspace. So it needs to respect that if v1 through vm, small v1 through small vm belongs to b for all vi belong to capital Vi, then their sum, which is small v1 plus until small vm, also belongs to b, just from the properties of b being a subspace. Okay, that's one property, that's one uh, relation we have. But the thing is, any element of v1, the vector subspace sum, is given by w1 plus plus wm for all wi belonging to vi, subspace vi, for I going from 1 to m. This is just the definition we had here in the pink, this definition. So then from before, we know that this w1 through wm is in B because any vector in B was given by just take each vector in each of those subspaces and add them up, and that has to be in V. And again, vi was, we had any vi in capital Vi. So from that we see that this w1 plus dot 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 plus wm belongs to B because each wi belongs to Vi. So it has to be in B. And we initially had that this sum was in the vector space, the subspace sum. So what that means is any element of the subspace sum, so v1 plus dot 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 plus vm, is a subset of B. So we have two things, that B is a subset of the vector's subspace sum, and the subspace sum is a subset of B. So it must be true, because of both of these have to be true, that B equals v1 plus dot 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 plus vm. And that indeed then, because B was the smallest subspace of V containing those subspaces, that the sum v1 plus vm must be the smallest subspace of V containing this. Otherwise, there's a contradiction. I hope you could follow this line of argument. This was a little fast, I admit. Maybe I'll give a quick recap. We assumed that there was a smallest subspace of V that contained those subspaces, and this was what the subsets would look like. That each Vi would be a subset of B, which would be a subset of the subspace sum. And by the definitions, by the properties of B being a subspace that contains Vi, it needed to also contain their linear combinations, which was v1 through vm belong to B, where each Vi was in the corresponding subspace. But then we also use the definition of the subspace sum, that any element of the subspace sum is just a sum of any vectors which belong to the corresponding subspaces. So w1 through wm, where each wi belong to the corresponding subspace Vi. Then from before we saw that such a combination has to be in B, because we had for any vi on top, this w1 through wn m linear combination had to be in v, but we said that it was first in the subspace sum. So each element of the subspace sum has to be in the set B. So we have this the subspace sum is the subset of B, but we also had from our assumption that B was a subset of the subspace sum. So we have these two conditions, and for both of them to be true and not give us a contradiction, B had to be equal to the subspace sum, which means that the subspace sum is indeed the smallest subspace of V that contains each of those subspaces. That's the entire argument in a nutshell. So please pause it if you, or rewind it if you did struggle to follow. And there's no embarrassment. Trust me, if it's a new topic, you take your own time to learn. So far, we know how to form large subspaces by taking the vector, the subspace sum. But notice they're given us a vector of the subspace sum. Let's call that V, which, because it's an element of the subspace sum, can be written as V1 plus dot 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 plus Vm, where each Vi belongs to capital Vi, the corresponding subspace. Suppose that subspaces V1 and Vm have the following vectors in common. So this set is common between V1 and Vm. We're going to call that the W vectors. So W1 through Wk. These K vectors are common between V1 and Vm. Then V can be expressed in two ways. You can, in this expansion for V, you can replace you can have a V1 equals W1 from this common set, and you can have the Vm equal to W2 again from this set, or you can flip them around. You can have V1 equals W2 and Vm equal W1. Both these permutations from the common set of vectors will be two expressions for V. So there's two distinct ways of writing V, and expressing V in terms of its subspace decomposition is really not unique. And this will be the point of the next discussion that we're going to have. That if we want to each vector of the subspace sum to be expressed uniquely and not have two ways like this of expressing it, then we must ensure any two subspaces have no common elements. That means we shouldn't be able to have a set of common vectors between any two component subspaces, like in this case V1 and Vm. Again, this is an intuitive way of looking at why we can't have a unique decomposition for any element in the subspace sum. Let's make it more rigorous. So suppose V1 through Vm are subspaces of V. Then the sum V1 plus dot 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 plus Vm is called a direct sum if each element of V1, the sum of the subspaces, can be written uniquely as a sum of V1 plus dot 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 plus Vm, where Vk belongs to the corresponding subspace capital Vk for all k going from 1 to m. And we indicate a direct sum. We differentiate between a regular sum of vectors of subspaces and a direct sum by doing this O plus symbol. We do a plus and encircle it like that. Okay. And here's the proposition with the direct sum. Suppose V1 through Vm are subspaces of V, then the sum of the subspaces is a direct sum if and only if the only way to write 0 as a sum V1 plus dot 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 plus Vm, where each Vk belongs to the corresponding subspace capital Vk for all k, is by taking each Vk to 0. So that means if you want to write 0, and 0 should be in the sum of subspaces because it's a subspace, the way to write 0 in the subspace sum, as as in this way, because each element of the subspace sum can be written as a sum like this. The only way to write 0 in terms of this kind of expansion is by taking each of these v1 through vm and setting them to 0 at the same time. Okay, so how do we prove that? Well, this is a bidirectional argument, so we have to go both ways. So in the first, we will assume that it's a direct sum, that v1 plus dot 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 vm is a direct sum, and then we will argue that we will show that the only way to write 0 is by taking all the component vectors to 0. And in the second part, we will assume that, well, this is the only way to write 0 in this form is by taking the component vectors to 0, and then we will prove that it is indeed a direct sum. So suppose the subspace sum is a direct sum, then by definition, it implies that the unique way of writing 0 as v1 plus dot 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 vm, where vk belongs to capital Vk, is by taking each vk to 0. Because this is by definition of a direct sum. You'd have to take each of them to 0, and then that would be the unique way, because it's a direct sum. We're supposing that it's a direct sum. We're assuming it's a direct sum. So this way is straightforward by definition of direct sum. Now suppose the only way to write 0 as v1 plus dot 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 vm, where vk belongs to capital Vk, is by taking each vk equals 0. We will now try to show that the subspace sum is a direct sum. So let v belong to let v belong to v1. We can then write v equals v1 plus dot 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 plus vm for some v1 belong to capital. We can write any vector that belongs to this subspace, this sum of subspaces, in terms of v1 plus dot 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 plus vm. We can do that, but then to show that this is unique, suppose we have another way of writing v, which v was an element of the subspace sum. Suppose there was another way, and that another way is by these u vectors. So u1 plus dot 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 um, where each u1 belongs to v1, and so on. Um belongs to capital Vm. Those are the two ways. Let's subtract both equations. So when we do that, we have a v minus v that gives us a 0. We have v1 minus u1. We're putting the brackets by the associativity of vector addition, plus dot 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 plus vm minus um. Now we assume that the only way, the unique way, the only way to write 0 as a sum like this was by taking each component vector to 0. We're going to use this because we assumed that in this direction we really have a 0 on the left hand side. So that means each of these components have to be 0. That means v1 minus u1 has to be 0, and so on until vm minus um, which also has to be 0. So that's what we have. Vk minus uk equals 0 for all k going from 1 to m. That's because we assumed that the unique way of writing 0, we're assuming that the unique way of writing 0 is by taking each component in its expansion to 0. So then you simply have v1 equals u1, so on until vm equals um, which means both these seemingly distinct ways are actually the same, which was, as desired. And that's what we had to show. So we've established an equivalence, an if and only if. We showed both directions. And I know this might be again a little fast to digest, but this is how we do it. Suppose u and v are subspaces of v, then, and this is our first theorem, u plus v is a direct sum if and only if, that's what the if and this arrow, bidirectional arrow, stands for, the if and only if u intersect w equals the trivial set or the zero subspace. So how do we prove that? It's bidirectional, so we have to prove both ways. So first, suppose u plus w is a direct sum. So then if v belongs to u plus w, uh, you can write 0 as v plus minus v. So we've just expanded 0 as, an element v plus minus v, which is the additive inverse of v. So in this expansion, v can be seen as coming from u, which, it makes sense because v belong to the intersection. So v belongs to u, and negative v also belongs to u, but we're treating it as an element of w, again because v belongs to u and w, so negative v belongs to w as well. So this becomes a representation for 0 as, a sum of vectors, one of which is in u and the other is in w. And we proved in the previous result that the unique representation of 0 in this kind of subspace sum is, if is and this is a direct sum. So a unique representation of 0 in the direct sum is if its components are 0. So that means v has to be 0 and negative v has to be 0, which are the same identical conditions. So we just have v has to be 0. And v was just an arbitrary element of the intersection of u and w. So that means u intersect w has to be 0. Now suppose u intersect w is trivial, is the 0 subspace. Then to show that u plus w is a direct sum, suppose u belongs to capital U and w belongs to capital W, and suppose we write 0 in as a sum of subspaces. So 0 equals u plus w for some u in capital U and w in capital W. Then we have u equals negative w. Now w belongs to capital W, so negative w belongs to capital W, and u also belongs to capital W. So that means u not only belongs to w, it also belongs to w. So u belongs to u intersect w because it belongs to both. And we assumed at the beginning that u intersect w was 0. So we have that u must be 0. And since u is 0, u was equal to negative w, so w has to be 0 as well. So this shows us that u0 is expressed uniquely in u plus w, and then by the previous result, u plus w must be a direct sum. And this box is for a proof that is completed. So what's the takeaway message from this proving this theorem? Is that if you have a sum of subspaces v1 through vm such that vi intersect vj equals the 0 subspace for all I not equal to j going from 1 to m. So all that means is any two subspaces in this subspace sum intersect only at the 0 element, then this subspace sum is actually a subspace direct sum. So a subspace sum needs to also have a trivial intersection amongst any two subspaces for it to actually be a subspace direct sum. That's the takeaway message out of all of this. So what's the example of a direct sum of subspaces? So let's take U, which is the xy plane, again an element of F3, such that x and y belong to F, and W is just the z-axis. So 0, 0, z belongs to F3 such that z is an element of F. Then F3 you can verify this, is just equal to u direct sum w. So f has been decomposed nicely into an xy plane and a z axis, and such that again you can check that their intersection is trivial, is at the zero. So they're indeed a direct sum. The other direct sum we have is, suppose Vk is the subspace of Fn of vectors whose components are all zero except in the kth entry. So what that means is, for example, if you have V2, that means everything except the second entry is zero. So we have just the second entry which is non-zero, let's call that x. Everywhere else is zero. So we have 0 comma x comma dot 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 0. And of course this belongs to, and I think I have the wrong brackets here. This belongs to Fn because of course it's a tuple of n elements, each of which belong to the field, and of course x has to belong to the field. Then Fn, of which each of these vk's were subspaces of, can be decomposed or expressed as v1 direct sum dot 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 direct sum vn. So it's a direct sum of n subspaces which are like one axis essentially. So you've broken Euclidean, you can take f to be r, you have Rn, the Euclidean n-dimensional space, into just subspaces which are just the axes, the different x, y, z. You'll have n axes because it's Fn or Rn. That's the kind of direct sum decomposition you have. And these concepts of decomposing vector spaces into direct sum of subspaces will be extremely important to us going forward. So I hope you enjoyed this video, guys. Like and subscribe to my channel, and in the meantime, peace out.